Okay, guys, so today we're going to continue on with our discussion of waves. I'm going to talk about basically 3 or 4 different things today. Then I have, since we're not in the lab, we're not able to do our experimentation with springs, I have 4 different videos that you're going to watch, and I've asked some very specific questions about what's happening in the videos. So I want to start out by talking about waves and energy transfer. So remember, a wave really is equal to the transfer of energy. We call it a motion of disturbance, and that disturbance is caused by energy. So there are some things that we need to remember. One, I just said, a wave is a disturbance caused by energy, and maybe we should even say energy transfer. We need to remember that energy is related to amplitude, and I can say that E for energy is equal to the amplitude squared. That's something that you want to keep in mind for later on. We've had maybe one question about that so far. There's probably going to have some more coming up. The third thing that we need to remember, or really not remember because you haven't had it before, it's something new. There's a characteristic of waves called damping, and it becomes very visible when you are watching a pulse wave hit a barrier, whether it's free or fixed, and bounce back. And that characteristic is called damping, and it's actually the loss of energy through time. That energy is lost over a period of time, and it's normally due to some type of resistance, some type of friction. So damping is the characteristic of energy loss that we see in pulse waves or any type of wave. Up to this point, everything that we've talked about, we've assumed that a wave could travel infinitely without anything to stop them. So we've been thinking about things, or thinking about waves, I should say, as perpetual motion, as just continuing on along the same path in the same direction. We haven't really thought about what's going to happen when they come into contact with a barrier. So we need to think about what's going to happen when that wave actually reaches a boundary. How's the wave going to behave? What's it going to do? Some of that depends on the type of boundary, so we're going to talk about that in just a little bit. When a wave actually reaches a boundary, that wave is reflected. So it hits the boundary and it's reflected back. It can be reflected in a couple of different ways, and that depends upon the type of boundary it hits. When I say boundary, I'm actually talking about it could be a fixed or a free surface. Sometimes a boundary can be something like changing from 2 different liquids. For example, let's say we're sending a pulse wave through water and we change it, our substance of travel through our medium, from water to, say, motor oil. There's a difference in the medium. The motor oil is more viscous, so as that wave hits a more viscous medium, that's going to have an effect on how it travels. And then if it happens to hit a free or a fixed barrier, it's going to travel back in a different way. So not only does the type of barrier matter, we have to think about, is it fixed or is it free? The type of barrier, the type of medium, that's pretty easy to figure out. Generally speaking, the more flexible, the less viscous a barrier, the easier it is, barrier or medium, the easier it is for the wave to travel. All right, so let's start by thinking about a wave at a free boundary. So when I have a wave that's traveling towards the boundary, I call that an incident wave. It's an incoming wave. And as we were to move into light waves, we would start thinking in terms of reflection and refraction. We just start thinking about things in terms of angle of incidence. What angle does the incident wave come in at? Since we're just talking about straight pulse waves right now, we just need to know that an incident wave is an incoming wave. If I have a free boundary, that means a flexible boundary, that means something that can move. then the incident wave will meet the boundary and it will be reflected back. It'll be called a reflected wave. The wave's actually sent back from the boundary. It's reflected back from the boundary. There's just multiple different ways to say that. When that happens, it occurs on the same side. We call it the side of equilibrium. I want you to think about equilibrium position like this. If I have a series of waves, this line right here, we've given it the name before of baseline. Baseline is actually also called or equal to equilibrium position. So if I come in as a crest, I'm going to be reflected back as a crest. So it's reflected back in the same phase that it goes in. If I go in a phase of a crest, I come back in the phase of a crest. That's if I have a free boundary. As opposed to a fixed boundary, sometimes a fixed boundary is shown like this, just as a straight line. Sometimes it'll be a straight line. Looks kind of like it has the tips of the arrow on the other side of it. That should tell you you're dealing with a fixed boundary when you're dealing with a wave. If I have a fixed boundary, the incident wave pulse and the reflected wave pulse, so the incident is the one coming into the boundary, the reflected is the one that bounces back off, if you want to think about it that way. They occur on opposite sides of equilibrium position. So that means that if it comes into the boundary or hits the boundary as a crest, it's going to bounce back off as a trough. If it comes into the boundary as a trough, it'll bounce back out as a crest. So it bounces back out of phase. Think of that as a bounce back or a return out of phase. So if I have a free boundary, we bounce back in phase. If I have a fixed boundary, we say that we bounce back out of phase on opposite sides of the baseline or on opposite sides of equilibrium position. Now let's look at this just a little bit. And I put these diagrams, I attached them to today's E-Day work so that you could see them. These two are pictures. They're just different ways to represent fixed and free boundaries. In this position, we've got a fixed boundary. It shows no form of movement along the wall. If I look at this rod, we see the loop around it, and the loop is open. It's a free end. It's a free boundary. That means that this has the capability, my rope that I'm sending the pulse along, has the capability of moving up and down. Up here, where I'm riveted to the brick wall, I have no capability of moving up and down. We see that before reflection, this would be called my incident wave or pulse. Before reflection, I'm traveling in as a crest. I hit the wall, and my reflected pulse comes back as a trough. So they are out of phase, is what I would say there. When I look at my free boundary, you can see I travel in, my incident equals a crest, and my reflected pulse equals a crest. So these guys are reflected in phase. The bottom picture, as I said, it's attached to this E-Day. It shows exactly the same thing. It's just a little bit different diagram. Here, I have a fixed end. I come in as a crest. I reflect back as a trough. Over here, I've got a free end. Notice it's hard to tell which is which from this diagram, so they've used words. I've got a free end. This is capable of traveling up and down. That's what the arrows are telling me, which means if I come in as a crest, I'm going to reflect back as a crest. Another way to look at this, yeah, I have one more diagram, and I also put this one on. Another way to look at this, you might see something like this. It shows the incoming wave as the blue and the reflecting wave as the red. And we have to look at that, and we have to see, is this a free boundary or a fixed boundary? If I'm coming in as a crest, if I have a free boundary, I would expect to come back as a crest, but I don't. I'm coming back as a trough. So this would tell me that I have a fixed boundary. So that's just another way you might have to look at those diagrams. All right. So I also want to talk a little bit about standing waves. Those are our pulse waves we've been talking about so much. Those pictures that I just showed you were all different standing pulse waves. A standing wave is actually a wave pattern that results when two waves with the same frequency, wavelength, and amplitude travel in opposite directions. So instead of talking about just one pulse wave, we're talking about two waves that are traveling in opposite directions, and they actually interfere with each other. But these two waves happen to have the same frequency, the same wavelength, and the same amplitude, which is a unique situation. So when I have a standing wave, it can actually appear to be, because it does happen, a wave that remains in constant position. That would be 100% destructive interference. It's always a wave contained by two fixed boundaries, and it results in two waves traveling opposite directions. In the end, there's no net propagation of energy due to the interference. When I'm looking at standing waves, there are two definite positions that are apparent on any standing wave. You just have to look for them and know what they are. When I have a standing wave, there's an area on the wave that's called a node. A node represents complete destructive interference. It's the point where there's actually no displacement and the wave is stationary. That's one area or region of a standing wave. The second is called an antinode, and it occurs midway between two nodes. So we've got two low points or two nodes that are very apparent. I'm going to show you a picture of that in just a minute. And in between those, we'll have a point of maximum displacement. The point of maximum displacement is where I would call that an antinode. And if I look at this wave series, E, A, and C would be my nodes. B and D are the antinodes. So node ACD, no displacement. Antinodes are B and D, and here I would have maximum displacement. This is just another picture, pretty much shows the same thing, shows it in color. Standing wave comes in. I have nodes, antinodes marked in the same way. And I think that's about it for this time. I did leave you some videos and a few questions. Go ahead and get those done, and I will see you at our Google Meets.